knowledge for our parameters, and that might actually pose a very big issue to traditional Markov chain Monte Carlo samplers, which usually do require some a priori knowledge of our parameters. And the last and most important motivation is that we are trying to develop an exoplanetary retrieval algorithm that is efficient, accurate, and portable to NASA's planetary spectrum generator, which is, you can find it online. It was developed by Geronimo, and it's open to anyone to use. And we want our exoplanetary retrieval algorithms to be portable to PSG. So what is a retrieval? So right here is just a very simplified graph of what a retrieval looks like. We take in our spectral data, and what we do is with the samplers, we actually run a set or a combination of parameters. And when we run a set or a combination of parameters, we run it using the forward model. And what the forward model does is it outputs what the data might look like with the combination of parameters that the sampler posed. And once we have that, or once we have that model, or what the data might look like with that combination of parameters, we bring it back to the space sampler, the probability space sampler, which will make a measurement of likelihood of whether that model fits the data or not. And it's basically a loop that keeps progressing between the forward model and the space sampler to find what we call the best fit for our data. So forward models. Forward models are actually, I dare say, the most important part of retrievals, because they are what establish or connect the theoretical meaning of the parameters to what we are observing in our data. So the reality is that with a forward model tells us, this parameter, this is what it means, and this is how it looks like when you run it in the data. And traditional forward modeling algorithms actually rely on very complex radiative transfer codes. They rely on algorithms that consist of running complicated and very time-consuming radiative transfer calculations for each parameter set that the sampler wants to try. Albeit these codes are usually very continuous and very accurate, so they do give us very, very good results. And some notable contemporary forward modeling algorithms include PSG, which that's exactly what PSG does. It outputs a synthetic spectra. And the same can be said for ExoTransmit, which was designed specifically for exoplanet forward modeling by Eliza Kempton. And in terms of how we can make our forward modeling process in retrievals better, some would say we can use grids. And this is something that I explored a lot in this project. And what grids are is someone actually uses, for example, something like PSD, a forward model code, radiative transfer code like PSD or ExoTransmit, and they run thousands and thousands of parameter combinations, and they run them and they create a grid. They create a database of the synthetic spectra that we got from those thousands of parameter combinations that these radiative transfer codes ran. And what we do with these pre-computed grids is we can actually use those grids as a forward model instead of having to run a radiative transfer code every single time we run a forward. Some pros of using this method is that it is definitely faster and less computationally intensive, which definitely means that these sorts of processes become a lot more available to a lot of people that might not have the same computational capabilities as others. It provides a lot of flexibility in the complexity of the physics involved, because basically the retrieval isn't running any radiative transfer code at that point. It's just taking it for a grid. So if you want to design a grid that gets really into the physics, that gets really complex, you're welcome to do that, and then you can use that grid in the forward model, and the forward model doesn't, and the retrieval, and then the retrieval doesn't really have to worry about the complexity of the physics, and in that case, it's very flexible. And it also generalizes the retrieval process. So if several people have different data and they're using the same grid, they can actually compare their results a lot better because they know and they're sure that their forward model was actually the same because they're using the same grid. Some cons of using pre-computed grids do include that grid parameters can be not finely sampled enough. Let's say that you're jumping from a temperature that is 1,000 Kelvin to temperature that is 2,000 Kelvin. All those temperatures in between do have significant value in how they change the data. And if we're not looking at that in the grid, we're actually missing a lot of information in our grid, which can make our fits not accurate enough. Some ways that we can work with this is high dimensional interpolation between grid points. And we do have a code that does that, which is called multiplater. And we have another challenge of using pre-computed grids is that there is no option for free parameters. If you're only using grids and you're not using other methods that I might talk about, we have no way of having free parameters in our computations. You have to have a set of parameter values for your forward models. Now, let's talk about samplers. So in terms of samplers, samplers are still very important because they are actually what sample all of the parameter combinations and provide us with our best fits. And sometimes they can even provide us with a very in-depth analysis of why we obtained those fits. Many different types of retrieval methods exist. There's Levenberg-Marquardt, which is basically a damped least squares method. We have optical estimation, Markov chain Monte Carlo, multimodal nested sampling. And here on the right, you guys can see a comparison of a retrieval performed by a Levenberg-Marquardt least squares method versus a retrieval performed by MULTINEST sampler. Aside from the fact that I spent a lot more time working on the graphs for the MULTINEST sampler, and that is apparent, you guys can also see that the fits for the Levenberg-Marquardt sampler are not as accurate because the sampler is a lot more simple in how it samples the data and how it samples the parameter space. And some comparisons of some of these methods have been done before. For example, Michael Lyon in 2013 actually did compare Markov chain Monte Carlo and optimal estimation methods for exoplanetary retrievals. And we kind of wanted to do something similar with two samplers that we have, which are diamonds and MULTINEST. And I will be talking about that now. So basically what multimodal nested sampling does is that instead of the progress of the sampler depending on a single likelihood value of the model fitting the data, which is what traditional Markov chain Monte Carlo samplers do, the progress actually depends on the mass and shape of the likelihood, which obviously provides a lot more accuracy for us. And some comparisons between MULTINEST and diamonds, I have wrote them down here, but I will kind of just do a little overview. So MULTINEST actually gives us a lot of backwards analysis of the sampler. So it outputs equally weighted posteriors as well as several other statistics that actually allow us to put down confidence intervals and look at other issues that the sampler might have run into. And MULTINEST is actually well established and tested in astronomy for several different uses, and there are several different papers that use MULTINEST out there, including for exoplanetary retrievals. Diamonds was actually designed for astroseismology. And for oscillating problems. So actually it was designed for a very specific case, but then generalized to be used as a sampler. And Diamonds does something that I think is very cool and innovative. And what it does is it reduces the number of live points with sampling evolution according to a reduction rate set by the user. And this can be very cool if the user does have an in-depth view about their fit and knows that a reduction rate might work very well with their sampling, making it a lot more faster and efficient. But it can also be a con, because if the user doesn't know very well about their sampler or the models that they're sampling, the reduction rate might actually be an obstruction to the fitting. So a little bit about my project timeline as a whole, because I'm speaking about a lot of general ideas, but definitely there's a lot of work that goes into these general ideas. First of all, I worked with designing a generalized binary format for any data grid and an algorithm that can read a specific spectra or parameter combinations at a specific location. So what this code does is it actually can do it's an algorithm that can seek a specific location based on a specific parameter combination. So that means you don't really have to read in an entire binary file or an entire database of a grid to actually find your spectra. You can go directly to the point, which makes our forward code very, very fast and very efficient. I wrote a specific forward model code in C. Wrote it in C because PSG is written in C, and we wanted something that could port easily into C. So I wrote a forward model code in C that uses this reading algorithm that I talked about, and I incorporated MULTIMODAL, which is a high-dimensional interpolator algorithm that an intern right before me, Carlos Munoz, designed, and I incorporated that to my forward model. And I also designed an averaging binning method for the forward model that averages points based on the pixel centers and widths that the user inputs. And these pixel centers, these pixels can be, pixel widths can be non-equidistant, and they can also, there can also be, it accounts for there being holes in the data. And I tested this whole forward model algorithm in C against literature for WASP-39b. So what I did is I took the Wakeford et al. 2018 paper for WASP-39b, which includes Hubble and Spitzer data for WASP-39b. And I took their paper and I looked at their retrieval, and I got the parameters that they, and I obtained the parameters that they got from their retrieval. And I used that to output a forward model using my code with the same parameters and with the same binning to see what I would get. And as you guys can see here, the graphs do look very similar. So that tells us that our forward model at least is working as expected. After that, I worked on integrating the forward model to the C diamonds code, and this part was very, very difficult because the C diamonds code is actually very involved. Giuliano actually helped a lot in this part by porting it to a C format that we could incorporate a forward model with. But even then, the diamonds code is so dependent on different libraries and so involved that it made this process very, very difficult. After we were able to integrate the forward model to C diamonds code, I designed a plotting scheme for the results from diamonds, which you guys can see here. And I ran tests for the diamond sampler plus my forward, and I documented the performance. And most importantly, we were trying to look at how long it took to run these calculations and get results. So I turned, basically, I turned my C forward model then into an executable, accessible and usable by Python. And I did this because we wanted to look at MULTINEST. And MULTINEST has a very straightforward Python wrapper called PyMultinest. And we wanted to run my forward model with PyMultinest and then test what we got. So I wrote a script to run the forward model executable from C alongside PyMultinest. And we designed, alongside Michael Himes, I designed several test cases with different signal to noise ratios and binnings, and I explain here how I did that. And I ran the PyMultinest tests with both the ATMO grid by Goyal et al. And Adam Smith's Rocky Exoplanet grid, which the paper for his is in review right now. And right here, we obtain a couple of times. So most importantly, we can see the comparison between times it took to run diamonds and PyMultinest, which are our two different samplers. Diamonds seems to be taking a lot more. And some of this is that, as I already mentioned, the diamonds code is very involved since it was designed for a very specific case. And then PyMultinest runs a lot faster, of course. And here are some pretty plots of results that I had with the test cases that we designed. Right here, this is a signal to noise ratio of 6.7. We do expect our future telescopes to have a little bit better signal to noise ratio, but it's still very important to test this kind of signal to noise ratio because it's very real in some of our data. And basically, you guys can see here the expected and the result values. I'm going to run through these because I do have a lot of test cases that I ran, and I'm gonna go fast through these. This is a signal to noise ratio of 10. What this plot is showing us is our data, our best fit model points, and the confidence intervals for our sampler, for the outputs of our sampler. And right here we have our posterior plots, which kind of show the point densities of the parameters ran. And we have, this is a 100 signal to noise ratio. So what I think I want you guys to take away from this is, as you see between these three plots, the better the signal to noise ratio, the better results we seem to be getting, the closer to our expected values we get. And this is because obviously less noisy data makes it a lot easier for the sampler to find the values that it needs to find. And now we're going to do something very interesting, which is the comparison between a very well sampled grid and a less sampled grid. So ATMO does have a couple of parameters that are not as well sampled as we would want or as we would hope, which also makes our results less accurate than, for example, this is Adam's grid. And this is the same forward model and the same retrieval process running different test cases with Adam's grid for rocky exoplanets. And as we can see, his grid actually has a lot more points. I'm pretty sure ATMO has around 67,000 grid points. Adam has upwards of 136,000 grid points. And this is a very clear, this goes to show a very clear result of a grid being finely sampled versus a grid where the parameters are not as finely sampled. And we can see that our results up here, the differences between our values and our results are a lot better for Adam's grid. And finally, a direct comparison of posteriors for MULTINEST versus diamonds. As you can see, this was for a signal to noise ratio of 10, which obviously our fits were not going to be very as perfect as we would want them to begin with. But definitely MULTINEST is doing a much better job for what we need than diamonds, which, there could be a lot of reasons to this that go very in depth to the design of the code of the sampler, which I generally do not know enough to go very in depth as to why some of these differences are being observed. But what we can observe is that for our case of exoplanetary retrievals, MULTINEST definitely is a better option for us. In terms of future work, we want to continue to test and adjust these methods and their accuracy and performance. We want to adapt the sampler chosen, or we could just leave it open to any sampler that we might want to incorporate to see in order to be compatible with the PSG source codes. And we want to develop a criterion for when a grid isn't sampled enough, because this is a big part of why some of our results look as they do. And I have showed it with our graphs. So we do want to develop a criterion for when a grid isn't sampled enough. And we want to add ad hoc PSG forward modeling when the criterion of being sampled enough isn't met by the user inputted grid. And finally, we want to integrate our full retrieval method that we work on to PSG. So that is the end of my year-long project. I do want to acknowledge all my collaborators for all their help, their advice, and their selfless reliability. I know I have reached out to you guys at god-awful hours in the night, and you still have responded to me, so I definitely want to acknowledge that. I want to thank my mentor, Geronimo Villanueva, for his constant support of me on this project and also outside of it. And I also want to acknowledge the PSD core team, the other postbacks at Goddard, and my parents for making this year a great one. And this quarantine just a little bit more bearable. I definitely wouldn't have gotten as far as I did without all the personal and emotional support as well as professional. And
thank you, Giannina. Excellent talk. So we're going to move to the next talks, but if anybody has a question, please go ahead. It's fine. I think it's better we go for the talks after the free talks. But great job, Giannina. Excellent work. Really, really cool. And we're hoping to put all this work into the PSG website. So all your nice work during this year will be captured on the website and for everybody to use. So Michael, can you take the screen now?
Yeah. Let's see. Is that working?
Yeah, perfect. Great.
Cool. So a lot of what I'll be talking about is going to be sort of building off of what Giannina was just talking about. So it's Bayesian inference still. So we're still doing retrievals for exoplanets, but instead of using interpolation, we'll now be talking about using machine learning in place of that as an alternative approach here. So sort of an overview of everything I'll tell you about here. I'm going to remind you of this problem for Bayesian inference or retrieval. I'll introduce machine learning, just very high level. We'll talk a bit about regression because that's how we're going to be applying machine learning is to the task of regression. And to do that, we'll be using what's called the neural network model. I'll finally tell you about integrating neural networks with your Bayesian inference. And finally, I'll talk about applying this to exoplanet retrievals. So sort of a broad overview of the problem here. You have some measured or observed data with some uncertainties. This could be an exoplanet spectrum. It could be some conditions inside of a lab apparatus. And you're ultimately trying to find out what are the underlying parameter values that would explain the data that you measured. And so you have some forward model where you'd have some parameters that can be used to calculate some simulated data. And then when you want to do the retrieval, you would have some observed data with the Bayesian sampler that will propose parameters, calculate some simulated data, compare it to the observed data, and it'll do that, thousands or millions of times. And at the end, you get what's called a posterior distribution, which in simpler terms is just the different likelihood of what values each parameter of your model might take. So I'm going to focus in on that model because, as I said, in Giannina's case, she was working with the interpolation, and here we'll be talking about machine learning in place of that. So you can really stick any model you want in there. So in this case, we'll be looking at machine learning. So these are algorithms that can sort of learn how to model some inputs and outputs of a data set. It doesn't require you to tell it what it's doing or what the data is. You just give it the data and it will sort of figure this out for you. There's many different applications. The one that we'll talk about today is regression, which I'll talk about more shortly, but you can use this for translating between languages, transcribing like written text into digital text, classifying an image as a cat or a dog, identifying a dog breed of some picture, tons of applications. A lot of them are in your phone. You have them with you all the time. And there's different sort of frameworks to perform machine learning. And the one that I'll be focusing on is what's called supervised learning. This is when you know the inputs and outputs and how they relate. So in the case of exoplanets, if we have some input atmosphere, we know exactly how to calculate the output spectrum. And using that knowledge, we can train a machine learning model to do that for us. And the sort of general workflow for that is you start out with some random model that does very poorly. It's going to take some inputs and make a prediction. You'll compare the prediction to what you know the answer should be. And then the model can update itself based on its error and how wrong it was. And you'll do this some millions of times. And at the end, you're left with this trained accurate model that you can give some inputs and it will predict out some outputs that will match very closely to what you would have gotten if you used your sort of traditional analytical formula. So regression. This is a statistical method that you can use to estimate a relationship between inputs and outputs based on some model. And so I think pictures are 1,000 words in this case. So I have some example data sets on the bottom here. And you can sort of see by eye that, a straight line might fit this data on the left, whereas this data on the right, maybe it's like a sinusoid, maybe it's quadratic or something. So if we were to fit a straight line, we can see it's going to mostly go through our points. But if we were to use the same simple model on this data on the right, it wouldn't look so good. You would obviously want to use a more complicated model that can capture how your data is. So maybe you want a quadratic, and that will now properly model your data. But what if you have a model that's too complicated to use these regression techniques, like in the case of exoplanet atmospheres? As Giannina was saying, these parameters that go into it sort of have correlations, they affect things in similar ways, and for that reason, it would be very, very difficult, if not impossible, to apply regression. Or what if your model, you could use regression on your model, but it's a slow model and you want something much faster? And so one answer to that would be using interpolation. Another answer to that could be using machine learning, specifically using neural networks to do the regression for you. So these neural networks they're very flexible functions with many parameters, and for that reason, you can use it to arbitrarily fit any sort of data you're interested in. This can have as few parameters as a handful to hundreds of millions and anything in between. So using that, you can capture all kinds of crazy behavior and data. Below here, I've sort of a basic schematic of a neural network. You would read this left to right. This first column here is sort of your inputs. So in this case, we have just 3 inputs. Maybe it's like a planet's temperature, some cloud properties, and some gas in the atmosphere or something. Each of these arrows coming out of each of these, what are called nodes, circles are nodes. These arrows denote some sort of math operation that's occurring between one layer's nodes and the next layer's nodes. And it goes through what are these called, or hidden layers that are sort of doing some math behind the scenes. And finally, at the end, you'll get some outputs that you might be interested in. Maybe it's the spectrum of the planet or something like that. To maybe put it more concretely, to give an example here, if you had, say, an algorithm that's learning to take a picture and find faces in the picture, your inputs might be the pictures themselves. The outputs would be, say, a cutout picture of someone's face in that picture that you're trying to get identified. And in the hidden layers here, what these features would actually work out to be are things like noses or eyes or mouths, things that we didn't tell the neural network anything about, but based on figuring out the problem, it's learning things to identify in order to make a proper prediction on the output. And in the simplest case, if you have just a single input and a single output, this goes right back to the linear regression case that we started on. So this can model everything from a line to something as complicated as radiative transfer for a spectrum emitted by a planet. So using this neural network inside of a Bayesian inference machine, so on the left here is the same plot from earlier that I showed, so showing the forward model and the retrieval, the Bayesian inference. The only difference when you're using a neural network is first you have to compute a big data set of spectra, so like the grids that Giannina was talking about, and that'll be using your sort of slow radiative transfer model. And then you can use train a neural network, which will produce this fast neural network model that may take milliseconds instead of multiple seconds. So factor of 100 times faster, maybe more. And then you just do your retrieval in the same normal way. You'd have some measured data. Your Bayesian sampler is going to propose parameters, simulate some, or make some predictions, compare it to your data, and then you get a posterior at the end. I wrote some software packages for this purpose. That's what I wrote here. So Marge is the neural network training, and Homer is the retrieval package. I'll talk about that at the very end if you're curious. But let's get into sort of applying this to exoplanet retrieval. So here I'll be showing mostly results from the ATMO grid of Goya et al. 2018. But I've also applied this to Adam Smith's grid from Smith et al. 2020. And what we sort of do is take the data, the grid, we train this neural network to be able to reproduce this grid much faster. And then we're able to perform retrievals within any of that parameter space of the grid. For test cases, we're going to take some of these spectra, we'll bin them down to more realistic levels of spectral resolution and some signal to noise ratio that's sort of representative of exoplanet data. So to look at an example of a result here, so this is a spectral resolution of about 100 and a signal to noise ratio of about 10. So this is what you might get out of something like Hubble and Spitzer and similar telescopes that we have available today. I'll first start on this plot on the right, which should look kind of familiar. This is the best fit spectrum plot, sort of like what Giannina was showing. The red crosses here are the measured data with uncertainty, and the black dots here are going to be your best fit model, with the dark to light blue regions sort of all of the summary of all the models explored as a part of the Bayesian inference. And you can see it's a pretty good fit. It's kind of a busy plot, but trust me, it's good. The best fit parameters are all pretty close to your true parameters here. On the left here is sort of the posterior plot. So I mentioned before, you have a posterior that gives relative information about the values of the parameters. So along this diagonal, you have sort of 1D histograms for a given parameter and all the values it might take. So up here is temperature. In this case, the true value is about 2500 Kelvin, and that's right about what the sampler is predicting. These plots below the diagonal are going to be pairs of points. So here in this top left one would be the pair of points for all temperatures and gravities explored by the sampler. And our red line or our red stars are going to denote the sort of true value from that we know because we're working with simulated data. And in general, you can see that it's able to accurately retrieve back the input parameters with the exception of C/O ratio and sort of metallicity here. C/O is just a hard thing to retrieve. This is talked about in literature and like Line et al. 2013, Drummond et al. 2018. It's just a hard parameter to infer because it doesn't have a big effect on the spectrum, whereas temperature and gravity have a much more measurable effect. And metallicity here, it's again hard to sort of infer this because it's not having the strongest effect compared to these other parameters, but it does a pretty good job getting like a 3 sigma detection. And then to sort of compare to the interpolation results from Giannina's code, you can see it's pretty comparable. It's peaked about a similar point for temperature. It maybe overestimates gravity a little bit, but it does much better on the metallicity than the neural network does. Again, on C/O, you can see the true value is right here on the very edge. So it's again, kind of underestimating that just like the neural network, and similar results for the haze and cloud parameters. And sort of to really sort of hammer home the takeaway from this, this plot here is the same sort of plot, but with 2 different results overplotted. In blue is the neural network, and in red is the sort of traditional way of doing this, which is much slower. And this purple color you see on all these plots is what arises out of the overlapping blue and red. And these posteriors match numerically to about 99%, give or take. And the neural network is able to get basically the same answer, but in orders of magnitude less compute time. So the traditional way took hundreds of hours. The neural network did it in about 15 minutes. And you can, for most applications, this is the level of speed increasement you can expect out of using machine learning within a Bayesian framework. So the summary to take away here, neural networks can really speed up your Bayesian inference by orders of magnitude. The software packages I developed are available online here if you're curious, you want to go take a look. And these features, we're working on getting that incorporated into PSG, like Giannina mentioned. Having these retrieval options would be really great so that anybody can go on and use these regardless of their compute resources. So that's all I got. If anybody has any questions, I'll take those now. Thanks.
Thank you, Michael. This was a great talk, and it has been, so just to tell, so Michael has been, he's a grad student at University of Central Florida. He has been working with us this summer, but he will be coming the next summers. So he's a good person to, he's an expert in NN, and definitely a person to keep on, if you have questions, he will definitely help you. And as the last question is coming to be, this is one of the things, the challenges we're trying to do. But I think we've been interacting. I got the package from Michael. The idea is to integrate that into PSG sooner, so everybody can use all these nice developments by Michael. So if anybody have any questions, please go ahead.
Hi, Michael. Can you hear me?
Hi, Josh.
Nice talk. I just wanted to ask, so which Bayesian inference technique are you using? Like, is it MCMC or maybe I missed it, or nested sampling?
Yeah, sorry, that's a good question. I didn't really want to get into all those details, but in this case here, I'm using MULTINEST. But my package, it has the option for MULTINEST, for ULTRANEST, for a few different MCMC options. And I'm adding more as I have time. So really the results are sort of equivalent regardless of which of the frameworks I'm using as far as I've seen so far. But yeah, there's plenty of options there. And in this case, I was using MULTINEST so that we could directly compare with Giannina's results, which we're also using MULTINEST.
Okay, good. Thanks.
Michael, one quick question. What do you see are the next challenges? I mean, once you nail down this NN for the forward and we maybe pick one of the samplers, what do you think are the next applicability of actually AI and NN in general for exoplanet retrieval?
I think right now we're, because of exoplanet data just being so low quality, we're sort of reliant on this sort of approach that I've described here. But sort of if we take a look at planetary science of what people are doing in the solar system, we can sort of see where exoplanets will go next. And there's been people that are applying these sorts of techniques, but more complicated versions of them that give spatial information to like Saturn. For example, they're able to do retrievals across the surface of Saturn in, you know, ridiculously short amount of times compared to how it would be traditionally done. I could see it being applied to things like getting surface data from Mars, for example. You could really, the possibilities are endless. If you have data that you know how to model well, but the model is very slow, you can apply this sort of technique. So whether it's analyzing rock samples to analyzing, you know, the atmosphere based on remote observations, it's all applicable.
And that is great. And this is more the value that to implement the framework for NN into PSG, so it can span as a tool for other people. Okay, thanks a lot, Michael. And we're gonna move to the next talk by James, and we can also get more questions after that. So James, can you try to share your screen?
Sure. Try here. Okay, can you see my screen?
Yes, yes, great. I think you can go ahead. Perfect.
Awesome. Hi, everyone. My name is James Mang. I'm a rising senior at UC Berkeley, majoring in astrophysics and chemistry. And this summer, as part of the undergraduate research associate in astrobiology program, I worked on modeling M-Earth atmospheres in transit under the mentorship of Avi Mandel and collaborating with Geronimo Villanueva, Michael Himes, Mike Moore, and Adam G.R.W. Smith. And so first off, what is a transit? As we can see in this video on the left, these planets and objects cross in front of their host stars. And in our case, we focus on Earth-like planets around M-stars. And so these planets block out some of the light from the star as seen in the dip of the curves. And hidden within these curves are fingerprints of molecules that can tell us more about the planet and its atmosphere. So in the video on the right, it shows how the light can go through the atmosphere depending on the wavelength and the molecules present. It can either be absorbed or transmitted. And so from these events, we were able to get some observational data points at different wavelengths depending on the telescope. But what can we really do with these data points? And so on the right here, we can see some quote unquote observed data in red points. This is just simulation of what different transmission spectra in blue here can look like. And we can see that some of these fit better than others. So this process of trying to fit this spectra is called retrievals. And in others, in order to create these simulated spectra, we use what is called forward modeling. And some things to notice here are bumps in the spectra. And so we call these absorption features, and in this case of water. And the base level of the spectra, I'll sometimes refer to as a continuum. I've removed the numbers from the y-axis to make this more general and simplistic for the explanation. But transit depth is really just the ratio of the surface area of the disk of the star blocked up by the planet's disk. And so in this case, we see that the continuum is moving up as the cloud top pressure decreases, which means as the cloud gets higher and higher, we see less features since it is blocking and reflecting more of the light. So the overall goal of my summer project is to design a pipeline starting from creating a whole set of different spectra by varying different planetary parameters to create what we call a grid. And then the pipeline then takes these spectra and some observed data and tries to come up with a model that fits it best using machine learning algorithm and outputs that Michael Himes designed to fit the most likely value for each parameter of the planet that our grid samples through. And so the purpose of this pipeline is to be able to prepare for future JWST observations, which will provide new sets of data. So in order to see whether or not this pipeline works, we use K218b as a test case. This is because there's been a recent study from Beneke et al. 2019. As seen in this figure from the paper, it shows that the retrieval spectrum and the model based on 20 observational points in white dots. And these are from K2, Hubble, and Spitzer. And so in the blue line, you see the medium fit, and the red line, their best fit from their MCMC algorithm. And so they also have the 1 sigma and 2 sigma region in the dark and light blue. Since there have been discussions suggest that K218b have water vapor and clouds, a deeper probe by JWST could provide insight as to whether or not there is liquid water environment beneath the atmosphere. So now that you hear me say forward modeling retrievals, but how do we get from that to these planetary atmosphere profiles that we want? So here I'll be briefly talking about each step of the process, but for the rest of the remainder of my talk, I'll be going through each individual aspect. So we start with this transiting event, as I said, gather the data for the observations, and then I start to design the process of the forward modeling grid, the various different parameters, which I will outline in the next slide. And these atmospheric profiles go through some radiative transfer calculations through the planetary spectrum generator, and we get these resulting forward modeled spectra. And then I use the machine learning algorithm to parse through my grid and create a model prediction. I can utilize this data gathered from the observations and do a best fit to the model prediction and constrain the parameters for the planet. For example, here we see a histogram showing the distribution of the cloud top pressure, and the dashed line is, dashed black line, sorry, is indicating the most probable value for this parameter. And the shading indicates the first, second, and third sigma regions of this distribution. And I'll dive into these plots more in the results. So starting from the forward modeling side, I had to do literature search as to what parameters affect the spectra the most and assumptions that I can make to reduce the size of the grid. So in the end, some general assumptions that I make when creating this grid includes an isothermal atmosphere of 250 Kelvin and surface pressure of 1 bar, meaning that the atmosphere is from 1 bar to 1 microbar. And we also assume a single absorbing species. So in this case, that would be water. And I have 2 different cases where we have hydrogen and helium as a background gas and hydrogen and nitrogen as the background gas. And also to note that this cloud that we have included is does not have physical cloud formation model. So we use a simple gray absorber with no coagulation, condensation, or any of that kind of physics included. I then sample through these different parameters in the table on the left with the different combinations, ended with a grid size of 26,250 cases. And then I fed these profiles to PSG, designed by Ronald Villanueva. And you can read more about this in Villanueva et al. 2018, to generate the planetary spectrum after performing some radiative transfer calculations. So on the right is an example of the atmospheric profile from our grid. So here we see the cloud top, and when I say we change cloud top pressure, this cloud will move up and down this atmosphere, and then when I vary the abundance of water, hydrogen, and nitrogen in this case, these abundances will move from left and right in this atmospheric profile. Just note, this is just a simulation for a simplistic model. More realistic profiles will be more complex than the one shown here. So here I show a sample of the results for the case where the planet radius is 2.2 Earth radii, a surface gravity of 16.61 meters per second squared, and a surface temperature of 250 Kelvin. So the top left varying the abundance of the absorbing species. The top right is varying the ratio of H2 as the background gas. The bottom left is varying the cloud top pressure, and the bottom right is varying the cloud particulate radii. So some key observations we see here is that as we increase the hydrogen abundance as a background gas, it pushes the continuum down and diminishes spectral features. And then in the bottom left, we see that the higher cloud tops show less spectral features and increases the continuum as we go up, as I previously explained. And on the bottom right, we see the varying of the radius of the cloud particulates changes the continuum, but spectral features remain at similar depth. And we see this tail off at the end due to Rayleigh scattering. And last but not least, on the top left, the most complicated spectra here we see is varying the different abundances of water features as the features go up, but then as you increase water abundances. But then at some point on the spectrum, we see that increasing molecular weight pulling this continuum down. Now that we have the forward modeling the grid completed, I can start the process of training the model predicted and retrieval side of the pipeline using the packages from Michael Himes and Himes et al. 2020, Marge and Homer. So with Michael's help, I started to use Marge, which separates the individual profiles into 3 sets, a test, validation, and training set to prepare the fitting model. And I was able to get this resulting best fit spectra here. So what you see here is the red points are the observational data that were used by Beneke et al. And with their respective errors. And the black points are the best fit and the model for each data point that we have. We can see also the sigma values and the range based on each set here in dark and light blue. And the residuals at the bottom simply show deviation from each best fit to the actual data. And so here I show what the results we get from Homer. So Homer then takes the trained model from Marge in the previous slide and creates distributions of what each parameter can most likely be. So here I have a histogram for each of the parameter with a dotted black line indicating the value that is the most probable value. So starting from the top left here, we have the abundance of water, the background gas ratio, planet radius, surface gravity, cloud top pressure, and cloud particulate radius. So on this slide, I show the results from the grid that has hydrogen and helium as the background gases. So here on the table on the left, I show a comparison between the values that I get for each parameter with the 1 sigma errors and the values that they have at Benneke et al. 2019. So I get a similar value and definitely inside 1 sigma range of the water abundance and mean molecular weight, which is really exciting to see. But less accurately, but still within the error range is the surface gravity. But we do slightly miss the planet radius in this case. And here on this slide, I show the results from Homer for the grid that has hydrogen and nitrogen as the background gases. And so we're excited to see confined histograms for most of the parameters, and at some values of the planet radius and surface gravity are close to the values than the previous model. And but we do observe differences between the cloud top pressure, which is still within 1 sigma range of the Benneke value. But the water abundance and the mean molecular weight of the atmosphere, which are a lot higher than the Benneke value, which makes sense because with nitrogen gas in the atmosphere obviously increases the mean molecular weight of the atmosphere, which in turn decreases the scale height of the atmosphere since it is heavier. So this makes the atmosphere less puffy, and we see more H2O presence in the spectra. So in this grid, it makes sense to receive a higher abundance of water in this case. So finally, just some key takeaways from this is that PSG is a really powerful tool that can be used to help in simulations for future observations, as well as retrievals. I've developed a full pipeline here that has 2 grids right now of 26,250 cases for K218b with water as the absorbing species. But I'll be continuing to expand this grid to include other absorbing species for K218b, as well as other MRs. And we are happy to see that we're able to train our model on a grid and use the observational data to retrieve expected planetary parameters based on literature values using these machine learning assisted retrievals of margin Homer. And finally, the pipeline is ready for future observations and characterization of rocky planets for upcoming JWST missions. And I'd like to thank Avi, Geronimo, Michael, Mike, Adam, and the URA committee for the support and collaboration this summer. Thank you.
Thank you, James. Really, really nice talk. And I'd like to say I'm impressed to see it. We've been talking about this, but you know, you did an amazing amount of work in a very short period of time. I'm impressed, I have to say. And just for everybody to know, I mean, he actually started from scratch. I mean, with most of the things he was talking about here, there were things that we were discussing, but he created the grid, defined the parameters, ran all the simulations, and even got the retrievals out. So it's pretty impressive. And I have to say, it also nicely complement the free talks because it shows how, you know, the grids are the meat for all this training for the neural networks that discussed by Michael, and all the retrieval packages that I put all this together to understand that Giannina was talking about. So all these components are actually need to be understood together. And I think after this summer of you three working together, I mean, it was really enlightening for all of us, because I think we are kind of getting a kind of a pipeline of how to do things. So really, really, really important work. So if anybody has questions, please go ahead.
Nice talk, James. So yeah, I noticed the radius was undershot a little bit in the retrievals compared to the Benneke value.
Right.
Would that have anything to do with where like they defined their surface at, you know, because there is that degeneracy between like the assumed where, you know, the radius that's assumed at some pressure level, and if that's a different assumption between the 2 codes, then you would see this sort of offset between the 2.
Right. And something that I've looked at in terms of comparing Benneke's assumptions in their retrievals themselves, they did actually make changes towards their stellar parameters as well. So their transit depth actually values did increase, and they also changed their planet radius, was taken from another paper. In terms of what possibility of other values, that other parameters or priors that could be affecting this planetary radii and how we retrieve it, we're looking at different possibilities of, for example, how the atmospheric depth and the scale height would be affecting this, as we see a closer retrieval from a lower scale height atmosphere, but I'm not quite sure about what other parameters could be affecting this right now.
Cool.
James, nice talk. I have one question. So in the same, the atmospheric retrieval, so the background atmosphere is H2 or H2N2, or both grids you have used here?
So in this case right here,
Yes.
This is from with using H2 and helium background gas.
Okay.
And the next grid is using a H2 and N2 background gas in this case.
Oh, okay. And when you use H2N2, then do you consider collision-induced absorption due to H2N2? Is that taken care of in the forward model?
Yes, that's included in the PSG calculation there.
Calculation. Okay, thank you.
Yeah, and I have to say, if anybody has questions, all these things, and the Giannina, Michael, and James are all in the SEEK and the PSG groups, Slack groups. They are moving into their projects, Berkeley, UMD, and UCF. So, but they have the email, so please contact them because they have learned a lot of stuff. And I'm also, one of the things about this talk is to connect them with you, and I mean, they're actually going to be good persons to ambassadors for all these projects. So please don't hesitate to send them emails and ask about this work. And if you have more questions, please go ahead.
Yeah, so I also want to say one more thing to our group here, since it's a pretty large group of lots of different backgrounds, of modelers and observers. If you would like to collaborate in in developing new strategies for forward modeling with PSG, with new physics, or new ideas about retrieval algorithms or things like this, our group is really open to really trying to make sure that we're integrated with SEEK, with all the SEEK team members and others. So please let us know. I think there's a lot of room to grow in the physics that we include in these retrievals and these forward models. And so we'd love to work together.
Yeah, and challenge thing, as we were seeing, is that you see, we may be able to integrate soon, the idea of the neural networks and the idea of the retrieval packages that Michael and Giannina were talking about. The next challenge is all the grids James was talking about. They are computationally expensive and they have to be computed. We need to have some knowledge about what we're looking for. So this is it's more like it has to be done for a particular set of data, and it's a bit more challenging. But one of the things we want to also work ahead is more than in the long run is to automate what James did in some sort of easy way that people should be able to, with more based on the physics restrictions, may create those grids without going into all the technicalities that we typically have to go through. But that's for the future, of course.
I have a question. It looked like the mean molecular weight that you get for the planet is pretty different to what was published, but the rest of the parameters didn't look massively different. And I'm not an expert in this. So how come the mean molecular weight for K218 can be so different that the other parameters are kind of the same?
Right. So specifically, I think you're assuming you talk about this case with the nitrogen as the background gas, because this one is the one that has the most drastic difference, and that's just basically because in the Beneke paper, they actually just use hydrogen and helium as the main background gas, with a lot of different less abundant species included in the atmosphere. And so in this case, because of the amount of nitrogen that I basically have hydrogen and nitrogen gas solely. So if 40%, for example, in this case, if I have 40% or 80% nitrogen in the case, and nitrogen has mean molecular weight of about 14, then it really increases that mean molecular weight compared to, let's say, just having hydrogen and helium, which would just be around like between 2 and 4.
Okay, thanks.
Yeah, but Tom, you have a good point, and what you can notice from this plot or this table is that the water abundance has to be much higher than the Beneke result. Almost more than a factor of 10 higher in order to essentially compensate for that higher mean molecular weight and smaller scale height. You need more water to then produce the same feature depth. And so if James skips back to the H2 helium one, you can see that here the mean molecular weight is more accurate and the water vapor abundance drops. That second to last row drops closer to the Beneke values. So I think one of the questions raised is, well, how robust is this assumption of H2 and helium, or essentially a light mean molecular weight atmosphere, based on the data being fit? And then you can bring in arguments from mass radius and other things, but you know, this is something that we have yet to really delve into. Is there something interesting to sort of look into that hasn't been explored in this question of how well constrained is the mean molecular weight of the atmosphere, essentially?
So Avi, just a quick question on that then. So if you're pumping up water in this high nitrogen case, what does that come out to in terms of a metallicity? Is that like times 100 or?
Yeah, so yeah, James and I were just discussing this earlier today, and the idea of metallicity is really based on the idea that you have a solar elemental ratio, right? And so it's really only applicable when you're somewhere close to a solar sort of overall elemental abundance. When you start looking at scenarios where you have 50% N2 in your atmosphere, and then a high fraction of H2O, it's not, you're beyond sort of metallicity is what I would say, because you don't have the similar fraction of iron or silicon or other things in your atmosphere. So it's clearly a dominant, a sort of secondary atmosphere scenario, or some scenario where it's been lost. H2 and helium have been lost in significant fractions. And so I can't answer your question exactly, Prabal, but I would say that it's not really in the regime we're talking about.
Gotcha.
But
one of the good things about the grid that James designed is that it's broad in scope and it has a lot of dimensions. So it allows us to explore this degeneracy. You know, we don't stick to certain things. So we can see them with our own eyes that, you know, you can feed the data with 2 possible scenarios. So I think the value is already there. And then we can start thinking, as you were talking about, guys, Tom and Prabal, you know, okay, what is the physics? And then as Avi was explaining, yeah, we can now pull out the physics, the science of the planet out of this. So it shows the power of these grids when you explore the parameter space broad enough. So I think we got a good set of questions, and I have recorded the talk, so we can always go back and, you know, try to you know, see the slides and get the things. But we've been very productive summer for the free students. So we have to really congratulate them on the great work, and let's hope we remain in contact, all of us, and they're still part of the Goddard family of exoplanet research.
And thank you, Geronimo, for putting this together and letting us, you know, present our work.
That's great. Thank you for presenting the nice talks, and see you soon. Okay.
great job, everyone. Excellent job.
Thank you for coming, everyone.
Yeah.
Bye.
Thank you for the talk.
Everyone.
Bye.
Thanks, everyone.